All right, so this is 3.6 absolute value functions. My dog is mad. Milkshake is mad because she is in the crate right now because she is loud and misbehaves. So if you hear her, just ignore it. This will be a very short lecture today, so you have plenty of time to practice understanding the absolute value function. So in its basic form, it looks, it looks like this. F of x equals the absolute value of x. And it is one of our basic toolkit functions, so we should be really familiar with this already. The absolute value function basically returns a number's distance from 0 on a number line. That's why everything's always positive in the absolute value function, because distances are only positive. So they actually become very useful in some real world problems. But the definition of the absolute value is we define it using a piecewise function, which we've already kind of looked at this previously, and here it is. And so, of course, for values in the input that are greater than or equal to 0, it just returns the same exact value. And for any values that are less than 0, aka negative numbers, it applies an additional negative to make that negative positive. And so, if you're looking at it like if we say, okay, let x equal, let's say 2. So if we have x is 2, so we're going to use this domain, and so that just returns, f of 2 as, just 2, the same as the input. But if we are using, let's say x equals negative 2, so we're going to use this domain because it is less than 0. And so f of negative 2 is actually going to be negative 2, which gives me positive 2. So that's kind of how that works. Usually a numeric example kind of helps us kind of pick that apart. So here's your first application problem. And so it's just talking about, determining the resistance of an electrical part. And in this case, we're talking about a resistor. And so they have certain operating parameters, resistance, capacitance, etc. And so, for my stats people, you know exactly what I'm about to say. Due to imprecision in manufacturing process, the actual value of the resistance or, whatever can vary from piece to piece, even when they're supposed to be the same. And so the best that they can do is try to guarantee that these natural variations in the manufacturing process will stay within the specified range. So that's plus or minus 1%, 5%, or 10%. And so in this case, we're going to suppose that we have this resistor, this part, rated at a resistance of 680 ohms, plus or minus 5%. And so we want to know the actual...
Rivertown Psychiatry.
They'll have to wait. Anyway, make sure you take care of your mental health, people. That's important. So anyway, and I guess, I don't know who that is on Facebook, but I guess we'll figure that out later. I should have put my do not disturb on, but whatever. Welcome to my life, y'all. Anyway, so we have this resistor that's ideally supposed to be 680 ohms, but due to these natural variations in manufacturing, it's going to be plus or minus 5%, and we want to know the values of that. And so the first thing we need to do is, figure out what 5% of 680 is. And so we could just do that by finding the percentage here, and we'll find out that that's 34 ohms. And so remember, the absolute value is the difference on the number line. And so we want to know, what the difference between the actual resistance of this thing will denote with R, and the nominal resistance, which, we've defined that to be 680. That's what we say it should be. Should not exceed the stated variability. And so should not exceed, that screams inequality, right? And so with the resistance defined again as R in ohms, we have the absolute value of the difference in the two resistances, the actual and the, supposed or nominal, should be less than or equal to 34, which is 5% plus or minus, right? And so this actually takes care of all of that. This next graphic just reminds you about what we saw in the previous section about transformation of functions. So here is the basic parent or toolkit function, y equals the absolute value of x. In red, we see it shifted 3 to the right. Then we see it stretched by a factor of 2 in the green. And then we see it shifted up 4. And so that's just a brief review. So we can use those transformations of functions to, you know, figure out the equation given a graph. And so for this one, you know, this is the key place that we're wanting to look at, right? Is this, because we know this started at 0, 0, and it's now at, you know, 3, -2. And so that means we went, you know, right 3 and down 2. And that's pretty basic. So at this point we have, you know, right 3 and then down 2. So we're kind of getting started. But we also need to look at the fact that normally the absolute value function would be, it would be like this, right? So over 1, up 1. But it isn't. It's actually going over 1, up 2. And so that indicates a vertical stretch by a factor of 2. So we're going to put this out front. And that's going to give us our, you know, we can look at all this, and you're welcome to go back and read this, but this is the equation that we just wrote right there. And then this only serves right here. This just says, hey, for certain functions, the absolute value being one of those, a vertical stretch and a horizontal compression are algebraically equivalent. And so you can see that here. That doesn't always happen. So, but that's just something to note, that you can do it both ways in some cases. And then we'll get to the kind of the last bit, is solving an absolute value equation. So we know that if we're given this equation, 8 equals the absolute value of the quantity 2x minus 6, we know that what's inside of the absolute value bars will be equal to 8 if this number is either 8 or -8. And so it splits into two different equations that we solve independently, because they'll have two solutions very much like the quadratic. And so then, you know, you just end up with two different solutions, and we include them both. So in that case, anytime you see an unknown variable appearing inside the absolute value bars, that's going to be an absolute value equation, and we're going to solve it in the same manner as I just showed you. One thing to note is that if we start out with this equation where the absolute value of A or whatever's inside there equals B, if B is negative, it has no solution. We have to be very careful for that, because there's no way to make the value inside of the absolute value be equal to a negative number. So given the formula for an absolute value function, find those horizontal intercepts of the graph, and that just means find the solutions, right? Whatever that may be. And then finding the zeros of an absolute value function, you can do this with shifts if you want. It's far easier just to do it by setting the function itself equal to 0, right? So that's exactly what you're seeing here. So we'll see, you know, instead of f of x is given to be equal to 0, so this would be 4x plus 1 minus 7. So we'll isolate the absolute value, and this will be 4x plus 1, and then we'll split it into those two cases. So we'll have -7 equals 4x plus 1, and we'll have +7 equals 4x plus 1. And then we'll just solve, you know, by the normal methods, and we'll end up with x equals -2 and x equals, you know, 1.5. And those are your two solutions for that particular absolute value function, and those were the location of its zeros here and here. As you can see, we solved that algebraically. Here's your problem set. Should give you a little bit more practice with transformations of functions like you were working on Monday. But here again is your answer key. As before, if you have any questions or concerns or want me to look at some of your work, that's fine. Just shoot me a picture or a message on Remind, and we can take a look.